cannot guarantee whether David Wallace would have answered your question. Good. Now, notice the following, another remark about this, another property of this ontology. Notice that there is a new sort of non-locality, namely the state associated with the union of two disjoint regions is not a function of rho A and rho B. Okay, if you know rho A and rho B, then that does not determine rho A union B. So, word for this is non-separable. So, it's a kind of, it's some sort of non-locality. It does not, it's not the same thing as Bell non-locality. It's kind of, in this ontology, it's just more immediate. It's something built in right from the start into this ontology before you look at any Bell inequalities or anything. And this is also different. In this way, this space-time state realism is different from the wave function realism. In the wave function realism, you have a sort of separability in the sense, in the following sense. If you think of just a function on 3 n-dimensional space as being the reality, then if I tell you what the function on some region A of configuration space is, and I tell you what the function on some region B of configuration space is, then you know what the function on a union B is. Okay.
You're talking about a single particle?
No. In configuration space.
Configuration space.
Okay, so there's a certain thing that can be said about wave function in configuration space that would be a certain analog of this property, and there it's the other way around. Good. So wave function realism has some kind of separability property, but we don't regard this as a disadvantage of the space-time state realism. Good. Now in the relativistic case, we think of delta as a region on a hypersurface. Good. Now some more remarks about this space-time state realism. One chapter deals with GRW theory, or more generally, dynamical collapse theories, and the consideration of whether this same type of ontology could be used for GRW theories. And the answer is this space-time state realism and GRW theory, they don't go well together. And here's what happens in that situation. Let's see. Here's a space-time diagram, x and t. Now think of a non-locality experiment. So here's a space-time region, here's a space-time region. Here we have 2 entangled particles. I mean, draw something like the word lines, but these word lines, of course, should not be taken too literally. It's just kind of, they should be kind of wall tubes or something. Some region where one particle is. So here's experimenter Alice, here's experimenter Bob. The 2 particles are initially in the spin singlet state. And now in these 2 regions, we have spin measurements in some directions that Alice and Bob choose. Okay, and now let's look at these 2 hypersurfaces. Let me give names to these hypersurfaces. Or maybe I want to look at 3 hypersurfaces. This would be lambda 1, lambda 2, lambda 3. Now, let's consider this region here. call this the region B2. So this is the region in Bob's lab on hypersurface lambda 2. Now the reduced density matrix of associated with that region, and now we're looking only at these two particles, is the following. In a collapse theory, when the measurement gets carried out and the wave function collapses. So since on lambda 2 this measurement here is already over, the wave function has collapsed to either up or down. So let's say it has collapsed here to down, and since it was initially in the singlet state, the wave function has collapsed here to up. So the wave function of the B particle is now in the up state. So this is the density matrix. Now consider region B1. So this is this region here. The Bob's lab on hypersurface lambda 1. There, on that hypersurface, no measurement has yet taken place. So we have this singlet state, and now if we take the reduced density matrix of particle B, we get 1/2 the identity. Good. So what happens here is that these two regions, we get very different density matrices. And now let's consider the case in which these two regions just overlap completely. So I can consider the same region either as part of lambda 1 or part of lambda 2 if I vary lambda 1 and lambda 2 a bit in such a way that they have a big portion in common. So the problem that arises here is if we just specify a certain region that's a subset of a hypersurface, then there's no unique density matrix associated with that region. So I have two options. Either I say the state of that region depends on which hypersurface I'm considering, or it means that with this region, just a kind of local piece of hypersurface, I cannot associate any state. Both of which may be felt to be undesirable options. Now the situation is different. So this is what happens with the space-time state realism in a collapse theory. The situation is different in if we have unitary dynamics, because then actually since there's no interaction, since the two are space-like separated, then actually varying the hypersurface on the A side does not affect the reduced density matrix on the B side. Next remark, narratability failure. Okay, so this refers to some consideration put forward by David Albert, and let's consider the following version of this. Again, we're looking at two particles, one in Alice's lab, one in Bob's lab, and let's say in this region, instead of, and we start again in a spin singlet state, and instead of spin measurement, we look at a spin flip. So F is, we just reverse up and down. So since we start with a singlet state, when we reverse spin on both sides, actually we get the same state. You may be worried about the minus sign. Well, okay, something can be done. Put a minus sign in the appropriate place in the spin flip, so you don't have to worry about a minus sign. So what happens then is that initially the quantum state is a spin singlet state, and then occurs the spin flip, and afterwards it's still the singlet state. So at each time, psi t is the singlet state. Now if you look at this in different Lorentz frame, then it's not true that at every time the spin state is a singlet state, because here, for example, on this surface here, the spin flip has occurred on one side but not on the other side, so you get a different state. So this David called the breakdown of narratability, meaning that when you narrate what's happening, that is, you specify the wave function psi t at every time t in one frame,